We're at 34. Let's give it another 2 minutes or so. Well, 1 or 2 minutes.
I think a slow start on Friday morning would be normal, even if we were all there in person.
Okay. People are tired. So maybe just a few reminders as we're waiting for people to join. The first lecture today is the third of Kev Abazajian's lectures on neutrinos and astrophysics in the early universe. The second one will be the third lecture from Andre de Gouveia on neutrino mass models. And then in the afternoon, Lisa Everett will give her fourth lecture on quark and lepton flavor physics. We have the coffee break as usual at 1:30, and then the discussion session at 3:45 will be Kev and Ben Jones, doing the discussion. Okay, it just broke 40. I think we should start because it's already 4 minutes past. Okay, it's my pleasure to welcome Kev Abazajian for his third and final lecture on neutrinos and astrophysics in the early universe. Please go ahead.
Great, thanks. Somebody said they liked my t-shirt, so I got my wildest t-shirt for the Friday lecture. Anyway, it's I don't usually wear these in class, but with Zoom it seems more appropriate. All right, so today we're going to talk more about neutrinos in the early universe and how they actually fit into observations of the high energy sky in X-rays actually. So turns out X-ray astronomy may be one of the best ways to probe neutrino physics. So we talked about this feature in before we get to the X-ray astronomy. Let's finish up on what we're talking about in terms of neutrino masses from cosmology, neutrino number from cosmology, and the basic feature, of course, is the fact that the shape of the power spectrum and amplitude at small scales or large wave number out here is what gets modified by the presence of massive neutrinos. Okay, and our limits used to be, you know, when the first cosmological results were about here, and now we're about here. Okay, and note that is that yellow line is very hard to tell its position from the white line, so you really need a different way of plotting this. And the reason why things have changed and gotten so much better in the past 15 years or so to 19 years, back in 2001, when I was a young postdoc at Fermilab, the power spectrum of the cosmic microwave background, which hopefully was covered in other lectures, was not very well known back then. This is the current model, benchmark model of cosmology, and the boxes are the errors. Okay, and this is from a review by Wayne Hu and Scott Dodelson, and I highly recommend that if you're interested in the physics of the cosmic microwave background and understanding the origin of the anisotropies and how they constrain cosmology. But anyway, so this is where things stood 20 years ago, and now this is where things sit today. Okay, and this is the title should be slightly different. It's from what will happen in the future. There's a forecast and data on here. So the next stage of CMB experiments is kind of converging around a single experiment called CMB stage 4, and those are the rectangles that go about with error around the models. They're basically the same benchmark model, and this is where the data is. The points with errors are the actual data today, and it's quite a bit different, right? It's this curve with the errors around it has changed to this curve, which is pushed way up here, because not only are we measuring temperature anisotropy now, we're measuring the anisotropy of polarization of that of the sky, of the photons on the sky, and you can decompose them into curl-free modes and divergence-free modes called E modes and B modes, and they tell you different information about the sky because Thomson scattering is polarized. Density perturbations in the CMB at the last scattering surface only create E modes, while B modes would be something either two other things. One thing that would be gravitational perturbations at early times, or lensing of the primary cosmic microwave background at late times. And so the CMB is sensitive to neutrino mass through the primary anisotropy, similarly through polarization, which is just another measure or an extra information about the primary anisotropy surface by giving you polarization data. But the last curve here is giving you information about, for sure, it's giving you information about the structure between the CMB and us today through lensing of that cosmic microwave background. And the reason why things are getting so much better is that detectors are getting better and experiments are getting better. So WMAP, which came out in 2002 or so, with its first results, sits up here in terms of microkelvins of experimental sensitivity of its detectors. And things have just kind of like a Moore's law have kept getting better and better. Planck is started about 2010. And the next stage, this includes both space-based and ground-based experiments. The next stage of ground-based experiments were in the past 5 years or so, or 10 years or so through this period. Currently, we're in the phase of stage 3 detectors. SBT 3G is ongoing. ACT, the third generation of ACT is ongoing. And Simon's, the Simon's CMB experiment is kind of fits in between these two. And it's kind of stage 3.5 or so. What's going on in terms of the past few years is this experimental sensitivity is increasing, and this is enhancing forecast and sensitivity to two pieces of physics that really drives the future of cosmic microwave background anisotropy studies. One is the understanding the scalar to tensor ratio from inflation, giving you the ratio of scalar perturbations to tensor perturbations. But the other thing is neutrino physics. And the two canonical parameters of neutrino physics are the number of neutrinos, as we know, and the mass of neutrinos. And so we sit about here at the end of stage 3. We should hope to see results from the stage 3 experiments fairly soon. Some results are coming out from SBT 3G and ACT, but not all of them have come out. Primarily not the final cosmological parameter analyses. And so the next stage is this, what's called stage 4, where we hope to get to milli-eV level of errors. And I did this derivation on the back of the envelope to get down to the 20 milli-eV level, and more accurate forecasting, actually also including this optical depth prior, which we could talk more about, but it's important. You could get to 15 milli-eV or so. And we're here, we're talking about 3-4 years from now or more. If when the surveys start getting underway, that we would start getting to this level of sensitivity. So one way that this plays into neutrino physics in general is through combining with other probes, primarily neutrinoless double beta decay, as well as tritium endpoint experiments. The mass of neutrinos through double beta decay is the y-axis here, and the cosmological sum of neutrino masses is the x-axis. And you could imagine that if there is a signal in neutrinoless double beta decay, it would give you information here, while cosmology would give you information here. The current limits are in gray. These are not one-to-one mappings, right? This is a different superposition of mass eigenstates than this sum is. Another way to look at it is the mass of the lightest neutrino versus the sum of the neutrinos. You can no longer use linear plots because you're getting at this milli-eV level. So there's two curves here, one for an inverted hierarchy model and a normal hierarchy. And these days, I guess this is called normal ordering versus inverted ordering. And this is a bit dated. It's about 3 years, a little more than 3 years old. But the current cosmology actually hasn't changed its limits that much. It sits at about this level because we're kind of waiting for the third generation of CMB experiments. And our expectation for Catron limits, Catron just came out with its new limits. This is what it's forecast to be at ultimate sensitivity. So it's going to constrain things here, but with cosmology, if we're in an inverted ordering, we would have the sensitivity. If the true value is this diamond, you would sit in this bar with the sensitivity of CMB plus other information, which is a galaxy survey called DESI, which is of course, important as well. It's really all of cosmology is dependent on both local structure surveys through galaxy surveys as well as CMB information. If we say that at this diamond, normal ordered hierarchy, which maybe is the theorist preferred model, then we would have this kind of sensitivity, CMB stage 4. So I've always had a 1 foot or maybe a few toes in the experimental community. So I've been involved with CMB stage 4 planning. All right, so the future, is other things that are going to happen in the future are lensing constraints. Lensing is basically the lensing of background galaxies by foreground matter, and then you see distorted images of the background galaxies. It's expected that Planck plus Euclid, which is a European space-based mission for galaxy surveys and also lensing surveys and supernova survey, it could also get to this milli-eV level. If you just include the neutrino mass as an extra parameter, you get to that level. You may say, well, we don't know the dark energy. We don't know the neutrino number. Once you expand this out, you get to maybe the 40 milli-eV level. And back in 2002, we showed that lensing is fairly sensitive to both dark energy and neutrino mass at the same time, although they're degenerate. And that's because both neutrino mass and dark energy, that is not lambda, suppress the growth function. And I mentioned this before, that basically effects of neutrinos are free streaming early on and also alteration of the growth function. So if you have sort of a zero mass neutrino model as this white line, adding neutrino mass suppresses that growth function. And W does a very similar thing. It suppresses the growth function. So with lensing, you're integrating over this. This is the weak lensing kernel. So with lensing, you're integrating over a wide range of redshift. And so you're basically integrating over this part of this growth function. And it's very hard to tell the difference between integral of these two curves over that range. So there is a degeneracy with lensing forecasts and with between dark energy and neutrino mass. This is another forecast from another future survey and lensing experiment called LSST, and they've now named the telescope to be the Vera Rubin Observatory, which is great. Although the survey is still called the Legacy Survey for Space and Time or something like that. So the neutrino mass is also going to be extremely well constrained through these forecasts, and as well as the effective number of neutrinos. There's other things on the way cosmologically for surveys. There's an experiment that has proceeded to the next stage of NASA planning called SphereX. It has an amazing proposed use to cosmology as well as galaxy formation. It's going to have a survey of 1.4 billion galaxies. That's B with a billion with a B, and 9.8 million are going to have errors, redshift errors through photometric errors of better than a percent, so of order 0.1%. And it'll have basically the single space-based experiment will have 2 orders of magnitude more K modes, meaning more modes of information in wave number space than the Sloan Digital Sky Survey, which is going to be it's very impressive. Actually, I don't know of any forecast for neutrino mass sensitivity from SphereX at this point. SKA is a 21 centimeter survey, which means they're looking for the 21 centimeter transition in neutral hydrogen, right? That's the spins flip from undergraduate quantum mechanics of hydrogen. Oh, there's a couple of questions here. I totally missed them. Why is the blue band different from the green band? Oh, this was in this experiment. Was it this one or this one? This one probably. The blue band is, I think I explained that. The blue band is different from the green band and from the, just whether the model sits here or sits here. Oops. Did not want to draw. All right. Yeah, it's whether the model sits at the top diamond or the bottom diamond. And then there's another experiment. Or another question, how were the two diamonds chosen? I don't know. I didn't choose them. They were basically chosen to be sufficiently well separated to be able to give the information of the sensitivity of the experiment, not so that these bands are not too close together, but also sufficiently far away from the current constraints. What will the redshift range be? That's a good question. I don't remember the exact values. There is a science book and science paper by Olivier Doré. It's a mission that's led at JPL where Olivier is. I'd refer you to that to find out. I think it's certainly higher redshift than the Cylindrical Sky Survey. I don't remember the exact range. SKA, as I was saying, is a map of 21 centimeter emission from neutral hydrogen. Literally, the proposal is to measure all gas in the universe between redshifts of 4 and 8. And the sensitivity forecasts for neutrino mass are quite ambitious, with from 3 to 20 millieV. This, of course, requires you to know the relationship of where the gas is to where matter is, because really it's matter clustering, both dark matter plus baryonic matter, that will give you the information about the clustering. So that's called biasing. We know that galaxies are relatively unbiased at large scales. That's what makes galaxy surveys useful. They are an unbiased tracer of the matter distribution. However, gas can be unbiased at some regimes, but is much more prone to potential systematic effects of mapping your observed thing, which is the gas emission, to the dark matter emission. So one of the things that I think gets misrepresented in kind of both ways in terms of neutrino cosmology. One is that, well, we've got such great limits for neutrino cosmology. Why should we even ever worry about doing lab experiments on neutrino mass? Like tritium endpoint and neutrinos double beta decay are a waste of time if we already know, say, we're going to have information on the neutrino mass at the 20 millieV level. So that is a problematic statement, because cosmology is a model-dependent science in terms of doing particle physics constraints. It really relies on an Occam's razor argument that the primordial power spectrum, for instance, that we talked about, is a featureless power law, or maybe has a little bit of curvature into it, which is called running. The pre-fireball power spectrum, the one that arises from inflation. It also, the forecasts typically only in limits on neutrino mass typically just, again, use an Occam's razor argument that only one parameter is extended beyond the standard 6 lambda CDM parameters at a time. So if you want to measure dark energy, you start varying W. If you're interested in neutrino number, you start varying N effective. If you're interested in neutrino mass, you start varying that away from 0 or 58 millieV, the standard numbers. And you also don't include curvature, meaning you make the universe flat in lambda CDM models. There's papers that have been led by Bharat Ratra and others that show that there could be, in some of these tension data sets, could be pointing towards the existence of curvature as being more preferred than any other extended model. And when you ask Bharat if this is just ridiculous to have curvature be non-zero, he points to W being present, that is lambda being present, as basically as ridiculous. So we should just go where the data tells us. And I think that's a pretty strong argument. The other thing is I pointed out that there's a degeneracy between neutrino mass and dark energy, which from my work on lensing, and the W here is -1 in lambda CDM. But if you, for instance, measure neutrinos double beta decay to give you a neutrino, a beta decay mass that's consistent with a sum of neutrino masses of say 60 millieV, that could actually give you, force you into a W that is less than -1. So if you've constrained this to be, there's a degeneracy that goes this way in the W neutrino mass frame. So neutrino mass, remember, suppresses power, and W, if it's more positive, also suppresses power. So if you have power suppression for neutrino mass, you can offset that by power enhancement with a more negative W. Okay. So anyway, that is a thing to constrain. So it's possible that in another model, some neutrino masses can be, this is a question from the chat box. So it's possible that in another model, some of the neutrino mass can be larger and cosmological constraint is not very solid, right? But we still need to satisfy the ground data. Right, so remember there's a tension data set that already says that the neutrino mass is 0.3 eV or something like that. Yeah, so if you extend your model to include dark energy plus curvature plus other things, or features in the primordial power spectrum, although I showed that that doesn't really relax things too much from the work with Nick Kanik and Richard Easter, and Grigor Aslanyan, and I forget the fourth author, but so anyway, but in that work we showed that the features in the primordial power spectrum don't work. But if you start relaxing things, the neutrino mass can be different from the minimalist interpretation of the data. So is an extra neutrino the dark matter? And this is the next topic we'll talk about. So the sterile neutrino as being dark matter, and I've mentioned this before, and because it ties into how neutrinos thermalize and how resonances occur in neutrino mixing in the early universe. And so I'm just going to go through neutrino mass. You've heard about this from others a lot, but I'd just like to just go over this real quickly. You know, neutrino mass generation is I don't know if it's the original hidden sector theory. That's I'm pretty sure that's not correct, but it's certainly one of the original hidden sector theories. And that simplest models of neutrino mass basically generate them from some very massive sterile neutrino, which could be tied to a seesaw model. And Andre de Gouveia, one of our fearless organizers, was one of the first to point out the phenomenological model for basically producing neutrino mass as being the new neutrino standard model. And basically by including Dirac and Majorana mass terms into the standard model of Abazajian. This is sometimes called the neutrino minimal standard model. And by this group, which basically posits that there's actually nothing beyond just this, and also related models by Manfred Lindner's group. And basically you put in two massive sterile neutrinos required by the solar and atmospheric mass scales. And I would argue this is the only hidden sector model for evidence for its existence, because you have to have neutrino mass generated in some way. And then since you have two massive neutrinos, and you could push this down to even a few GeV. If you have two massive neutrinos, what are you going to do with the third? If you have symmetry in the two massive sterile neutrinos. You could have a third massive sterile neutrino. And that one, since there's no need for it in terms of mass generation, it could be anything. It has complete freedom. And in the simplest formulations, the lowest mass light neutrino is unbounded from below. So the mixing of the lightest sterile neutrino is also unbounded from below, because the mixing angle for the active neutrino with the lightest sterile neutrino goes as this formula for when you diagonalize. So that's nice, because you actually need very small mixing angles in order to create dark matter. And so, this is a neutrino TASI, right? And one thing about neutrino physics, I think it sometimes doesn't get as much rah-rah, kind of excitement within the particle physics community. So if you just took this slide and changed every single sterile neutrino to a dark fermion, then you would be one of the cool kids working on beyond the standard model building, right? And nothing actually changed in this slide other than the word, because the sterile neutrino is a dark fermion, right? So anyway, so if you can just say you work on hidden sector dark fermion models, and then you're like the rest of the model builders, right? Anyway, there's more evidence. In essence, there's a question here. A neutrino is basically just an extra fermion, which is a standard model gauge singlet. That's right. That's right. So a sterile neutrino is an extra fermion with a standard model gauge singlet. That's right. So there's more evidence that there's a lot of neutrinos. Here's a rock band from Russia called Neutrino, and clearly they think there's 6 of them. So anyway, so I showed this before. Maybe there's 6 neutrinos, 2 dealing with short baselines, and a 6th that is dark matter, or that you could just ignore the short baseline results and say that the 4th neutrino is the thing that provides dark matter, and the other 2 sterile neutrinos are even higher scale, somewhere way up here, providing the mass generation mechanism for the lighter neutrinos. So quickly, the history, and I don't, since this is a pedagogical, I wanted to include it. Basically the model, or the idea of sterile neutrinos as dark matter, actually dates to the 1980s, and they were called sterile neutrinos. And there were in some reviews by my colleague at UC Irvine, Virginia Trimble, from the mid 1980s. And that I never found what papers she was referring to that were calling it the sterile neutrino, but it was this work by Keith Olive and Michael Turner in 1982 that really weren't truly sterile neutrinos as we think of them now. They were really super weak neutrinos that had some coupling that was weaker than weak, and they basically just have earlier decoupling, and that abundance is set by the standard dark matter production mechanisms of freeze out. So sterile neutrinos, as we know them now, were really, as dark matter, were hypothesized by Scott Douglas and Lawrence Woodrow in 1993. They have no standard model interactions beyond the mass terms, and when you include the finite temperature effects we've talked about, you get a lack of thermalization at early times, and they pointed out that it would be warm dark matter. Then there's shortly after that, about 5 to 6 years after the Douglas and Woodrow, she and Fuller pointed out that you could get resonant production of the same kind of neutrino if you have a non-zero lepton number in the universe. And this, I told you I went to TASI 1998, so I was a graduate student, and I was actually kind of young. It was only my 2nd year in graduate school that I went to TASI, but it was neutrino one, so I had to go. And so I was working in the same group with George Fuller and Zhengdong Shi at UC San Diego, and they were working on this stuff, and Zhengdong Shi was really supportive, and he said, you really should we just did a very rough calculation, because they were doing single momentum mode calculations just to point out the mechanism. And encouraged me to work on this as a project for my graduate work. And if you think about these two models, there's basically just a single parameter that ties them, which is the value of the lepton number of the universe. So you can smoothly transition between these two models with that parameter. And so that's what I worked on. And we did a full momentum space calculation. Both of these were single momentum mode calculations. We know they're thermal, and the resonance is momentum dependent, so it's more appropriate to do that. And we also included the effects of the QCD transition through that period of production, as shows important. We also looked at constraints, and it turns out that constraining sterile neutrino dark matter is done by lots of things: cosmic microwave background, Big Bang nucleosynthesis, but the best constraint comes from X-ray astronomy. And this was back in, the original work was in 2001, early 2001, I think during January we put out the paper, and in late 2000 was when the first X-ray astronomy results were coming out from the Chandra X-ray Space Telescope and XO Newton. So we've already seen this. We've got a density matrix formalism for the evolution of neutrinos in a bath of thermal bath. Here epsilon, I've rewritten it instead of PT. I've written it as E epsilon versus time, where epsilon is a expansion invariant or general relativistic invariant in a Friedmann universe, which is the momentum over temperature. So this is the density matrix or P vector formalism, and it turns out you can rewrite all of this to be a quasi-classical Boltzmann equation. So you put in all the physics of this into just studying the diagonal terms of the density matrix, which are the distributions, the F distributions of the neutrinos. So here we've got a very simplified view of what's going on in the Boltzmann and density matrix evolution. You've got neutrino production due to some weak interaction at time t equals 0. This isn't the age of the universe. This is just the time after a weak interaction. So a weak interaction happens at t equals 0. And if you had no oscillations, the probability of neutrino flavor state A continuing as A would just be constant over time and space. But you have oscillations, and we're talking about oscillations for sterile neutrino dark matter at the level of 10 to the minus 11, okay, in amplitude. Remember the single parameter here of amplitude. However, if you have interaction, if you have a neutrino that is just propagating here in space and time, and it almost immediately on these scales, on the oscillation scale, almost immediately interacts with the plasma again, it gets reset to being a flavor state, an active flavor state, because its probability is very close to 1 with these rapid interactions. So this is called the quantum Zeno effect, where basically the interaction rate is very rapid relative to the oscillation length, okay? Or the interaction length is very small relative to the oscillation length. And parameters are included through the damping terms. Then there's also the you could actually start having the interaction length be comparable to or larger than the oscillation length. And then that you get what is effectively collisional production. So the thing that keeps sterile neutrinos from being produced is also the thing that eventually produces them, and that's interactions. So, but the interactions have to be just right, beyond the, getting to the level where the probability of it being a sterile state is non-zero. So how do you solve a Boltzmann equation? What is a Boltzmann equation? And one of Feynman's old jokes is that every equation is actually very easy because it can be reduced to this equation, right? And so that's the Boltzmann equation. A slightly more complicated version of the Boltzmann equation is that you have a Liouville term on the left and a collision term on the right. This gives you the evolution of the phase space distribution in cosmology due to expansion or phase space in general. And the collisional terms tell you how things evolve due to interactions. And so this is what it looks like for those diagonal terms of the density matrix. In particular, you're interested in the diagonal term corresponding to the neutrino density. And that is given by this on the left-hand side, which is the Liouville term for expanding homogeneous isotropic universe. And the right-hand side is this sum of a bunch of things that are going on. This is just a phase space integral. And the two key things is the matrix elements of the interactions. There's Fermi factors. But the two key things are these probability of conversion. In a lot of work I use the muon neutrino, but any flavor works. And we've seen this already, that basically the interaction or production rate of sterile neutrinos goes as that's matter effective mixing angle times this interaction rate. And again, it's this t to the 5 upstairs, and then inverse t squared, and then t to the 10 downstairs. Now I've included something that has not been there before, which is damping. This suppresses the conversion when this is large, and is actually also the same scaling as the thermal potential. And comparing it, like you always do as a good particle cosmologist, with the expansion rate to find out if this rate is causing thermalization of this new particle. And you can find out when it thermalizes at a certain rate, which is when gamma over h goes greater than 1. But you can tune the mixing angle. You can argue that it's fine tuning, but it's only a single parameter. So maybe you're just doing a prediction for what the mixing angle has to be. In order to get gamma over h to not be 1, but to be just enough to be, say, 1%, in order to get to the level of producing the dark matter at what is observed. So here are curves of gamma over h in simplified models with just this constant background. They're just smooth curves. This gamma over h, well, this is for a fixed mixing angle too, so they all go to the same low temperature gamma over h. But they peak at different temperatures, and so for 1 keV you peak at close to 100 MeV, and at 10 keV you peak at 230 MeV or so. But this is for the sterile neutrino mass, right? So right around here, though, is the QCD transition, which I'll show in a bit. But other things that could happen is the fact that you have resonances, right? So you've got this term where you can get cancellations, and then high production. Damping can still affect things because you're in a collisional regime of production and not in a MSW, pure MSW. And the neutrinos are never in equilibrium as a result of this gamma over h being tuned to just give you just the right amount. You've never have a point where gamma over h is 1. Right. So as I mentioned, the QCD transition is here at about 180 MeV. And that affects things quite a bit because the number of degrees of freedom and the background evolution of the plasma are changing rapidly during that interval. So in resonant production, the original Sheen-Fuller 1998-1999 paper showed that the momentum, if you have a Fermi-Dirac distribution for the active neutrinos, the sterols would be populated in the low momentum regime of that distribution due to the resonance proceeding from low momentum to high momentum, as we showed yesterday. And so you can work out the evolution of the position of that resonance, and it looks like this. Basically, you start depleting lepton number when the resonance gets close to finite amounts of the distribution. And so as both the lepton number decreases and the temperature of the universe, well, basically as the lepton number decreases, the position of the resonance increases. And it's offset by the temperature here as well. As that it continues also, so as temperature of the universe decreases, the resonance also goes there. Can I interpret this as a Friesen mechanism? Yes, this was Friesen before Friesen was cool. This is definitely a freeze-in mechanism, and it wasn't called that at the time, though. It is definitely a freeze-in mechanism. So the work that was done back in 2000, 2001, and then I actually also did some more work on more precise calculations of the production in 2005. In 2015, I was collaborating with two folks that were at Caltech at the time, Teja and Francis Yan, and also Chris Hirata, who had recently moved from Caltech to OSU, Ohio State, on a project. And Teja was a graduate student at Caltech at the time, and Francis Yan was a postdoc. And Francis Yan and Teja had pointed out that the hadronic processes could redistribute the lepton asymmetry collisionally. And so holding all of the lepton number that was done in the original calculations as being in one flavor doesn't work. It will get redistributed. And so that was included in this work that they proposed and completed. And so we also included a more accurate neutrino scattering database, and including momentum dependent scattering. And we updated the time temperature evolution of the plasma and updated the numerics. However, I think it's still in Fortran 90. So these following reactions will redistribute lepton number, right? You can, if you have an lepton number nu mu, it'll get redistributed with nu e with leptonic and hadronic interactions. And the lepton numbers, the quantum numbers, are related to chemical potentials with this what's called a susceptibility matrix. So it's going to convert the lepton number through this evolution description, and so you'll get an alteration of the lepton number with temperature due to these effects, and that was pointed out by Teja and Francis Yan. Sounds like this might be a big effect, and it is important, but it's not overwhelming. The potential does get altered due to the presence of these new effects. It gets suppressed, right, as you would expect when you redistribute the potential or the number. Another thing we included, and this is a heroic effort by Teja, was including the more exact neutrino scattering and momentum dependent on interaction rates for all of the neutrinos. And this is a temperature and momentum dependent thing. So the rates of all of these processes had to be calculated from high temperature down to lower temperature where production occurs. So the calculation then basically included the fact that you have leptonic interactions and hadronic interactions which are much higher, particularly the hadronic rates, much higher at high temperature. So increasing temperature is this way, but increasing time is this way. So the total interaction rate is the solid white line, but we don't know exactly the nature of the quark-hadron transition. It could be more steeply falling as the solid line is, or it could be a softer transition as the dashed line is. So we explored, and this is this is softer than you would expect, but it could be that soft. So we did a wide range of potential thermal histories for the quark-hadron transition, which also alters the amount of scattering quarks that are in the plasma at the time. So once you put all this in, then you get the momentum distribution of the sterile neutrinos that are produced over a wide range of masses and mixings. So here we label, so once you specify either the mass of the neutrino or the mixing angle of the neutrino, there's the other number is specified. So here we specify the mixing angle, and the mass is set to produce the right abundance of neutrinos to be the dark matter. And so these are the phase-space distributions. Fermi-Dirac is the dotted line here, and these are the phase-space distributions of the sterile neutrinos produced. And if you alter the Quark-hadron physics, there is some dependence, but it is not drastic. It is not a massive dependence within those bounds. So why do you care about the phase-space distribution of sterile neutrinos produced at that level, right? We're looking at these small effects. Let me go back, I'm trying to go back here. If you're looking at these small differences between the phase-space distribution, why does this matter? And that matters because the phase-space distribution affects structure formation. And so really this is a question about cosmological structure formation when you include sterile neutrinos as the dark matter. So remember this plot, the power spectrum is this featureless thing that gets bent over by fireball physics because the, oh, there's a question here, I missed that. Were these calculations for resonant production made with all 3 generations of the neutrinos? No, and it's because the density matrix is really nice for looking at single, 2 neutrino states, a single oscillation mechanism. If you were to vary it, if you were to include other things, it would, you could separate it out so that the scales are sufficiently separate that you have, say, mixing with a mu neutrino and a tau neutrino and an electron neutrino. Actually, I guess, if the mixings were sufficiently different, then only one of them would dominate the production. But it would be a lot of work to actually put in all 3 generations mixing with the sterile. I don't think it'd be impossible, but it'd just be more work. So this is our power spectrum given by whether the modes are entering at during radiation domination or matter domination, and what happens with dark matter and sterile neutrino dark matter, any kind of dark matter that has a thermal nature or thermally produced and has a non-trivial velocity distribution, is that it affects things on this scale. And the question that there's asked at this small scale, large wave number, is whether there's something going on with small scale structure, cosmological small scale structure. And there's been interest in this since the late 1990s, that potentially there's a cutoff in the power spectrum, and here's that same power spectrum. Now we're just looking at the tail end of it, not the full hump. But if you were to suppress power on these small scales, you could potentially alleviate some issues in small scale structure. This has been of interest for over 20 years now. And this suppression, this is a question, sterile neutrinos are warm dark matter, so they're ruled out. Well, is the blue curve right next to the dashed, or the cyan curve right next to the blue curve ruled out? Certainly not. But other models, this one is for sure the cyan curve over here. So where is the limit for structure on this range? And so this is work that I did back in 2005 to more precisely go from the production calculations to the structure formation results. Okay, so why are we of interest in this power spectrum? Well, this is a description of clustering, right? It's the 2-point correlation function, Fourier transform. How probable it is to have one lump or overdensity of matter relative to the position of another. And this is what it describes. So here, it's not very probable to have any clustering if you suppress the power. And so I did the calculation for the production of sterile neutrino dark matter back in 2005, and also did the Boltzmann transport of there's a Boltzmann transport of sterile neutrino production, but there's also the Boltzmann equations that govern the evolution of perturbations in the early universe. And so those are done by packages like CMB-Fast or CAM, and I used CAM, which was new at the time. And basically you can find where the measurements constrain this thing. And if you look at what is best to look at in this range. It's the Cylindrical Sky Survey Power Spectrum, which was measures at large scales, doesn't provide much information. It's really the Lyman alpha forest, either from the Cylindrical Sky Survey or from the VLT telescope or from Keck. Those at the time, the Lyman alpha forest was one of the best ways to constrain this. So the Keck points are the blue points and the VLT points are the green. So you might say, well, okay, so this is where the potential limits are. And I didn't mention this earlier, but the red line and the two red lines here are different points at which the limit of the free streaming is. Okay, so very aggressive limit is that it has to be colder than this red line, and a more conservative limit is that it could be as warm as that red line. Okay, but cold dark matter is neither of those, right? Cold dark matter, if you extend it out, goes out to a wave number not of 10 or 100. The cutoff is at 1 million. Okay, so and you get this cutoff in WIMP cold dark matter because you still have scattering of cold dark matter, kinetic scattering, which erases structure at that scale. And this is instead of being at dwarf galaxy scales, which is where you are over here, you get down to Earth mass scales for things. So this is where canonical cold dark matter sits. So even cold dark matter is not perfectly cold, at least not WIMP cold dark matter. Axion cold dark matter is colder. Simulating the universe's structure. So we've got that power spectrum, and that is what goes into then mapping, or basically calculating what is going on in galaxy formation. So we've got this power spectrum, and remember, this is a statistical distribution of density fluctuations on average in the linear regime of perturbations. And you need to take this power spectrum and realize it in a simulation. And so you need to create a distribution of matter that has the statistical properties of this power. And what you do is what was done originally by Shendaran and collaborators using a method that was originally developed by Yakov Zeldovich. It's called the Zeldovich push, or a Zeldovich approximation. You give a grid of particles, and this is from one of the original papers. You give a grid of particles a push in a certain direction and magnitude that then it provides the power, or this distribution has a power spectrum that is the growth of this power up until the time at which you do the push, which is still in the linear regime. So you've basically just solved the growth of structure in the linear regime in a particular realization. Then you take these points and then you let gravity do its thing. And then you just turn on gravity. Of course, I'm simplifying it, but you let them attract to each other and then follow their evolution to see the growth of nonlinear structure. And so this is the growth of a Milky Way type halo done by a group at UC Santa Cruz called the Via Lactea simulation. I like this because you could see the structure, the small scale structure in full glory around our Milky Way. And you get this very high density central region, and then you get these dwarf halos or sub-halos coming in that harbor dwarf galaxies, or could be dark. And they are all around the central overdensity. This is logarithmically, the brightness is logarithmically plotted. So this is much, much more dense than the other outer regions. So that basically gives you the starting conditions for simulations is the linear power spectrum. You feed that into the initial step, realization of the initial step of simulation, and then you evolve the simulation. So if you have less power, on small scales, there's less of a push of the particles on with small scales. There's more of a push with big scale pushes. You would get less power on small scales. You would get less structure on small scales. And this is from work by Carlos Frank's group. And one of the things that that it was thought that this could solve is the properties of local group galaxies. In particular, what was called the too big to fail problem. This is back in 2011, 2012, when the banks were too big to fail, and also galaxies that are produced in simulations should not fail at forming, well, the halos, very massive, dense halos should not fail at forming galaxies, okay? And so in CDM, that seemed to happen. These are simulated halos, while the points are the observations of our local group. So the observations should scatter about the same way as the curves. You can only really measure the circular velocity at one point for the observed galaxies well, but you know the circular velocity for all over a simulated galaxy. And all of these things up here are massive failures. And this is both too big to fail and massive failures is language from Mike Boyle and Colchin, who was a postdoc at UCI and now faculty at UT Austin. And in warm dark matter, there are no massive failures, and nobody wants to be a massive failure. So it seemed to be at the time that warm dark matter is a good solution to this. But the question is, oh, and one thing to mention here is that at the time there was interest in warm dark matter as being a solution that the 2 keV scale for a thermal particle, warm dark matter, is able to match all the observations of Milky Way satellites, including the total satellite abundance, the radial distribution, and the mass profile, meaning they're too big to fail. And so we talked about this at the discussion last time. What's the relationship between particle mass and warm dark matter effects? And that is that, so, you know, with 2 keV, if you want to get 2 keV, what does that mean? It's not actually 2 keV that you're interested in. It's that point at which you have suppression of the power, right? So here's CDM at, for P of K versus K. And warm dark matter, I should have made that blue, I guess, because it's cold. But let's make warm purple. Purple cuts off here, okay? So it's really the position of this cutoff, or the length at which free streaming occurs, to wipe out structure. And so that's given by this equation, which is again just an approximation for that length. You really need to put everything in. Another thing that's important is the Kozak-McClellan bound. You can't have fully thermalized neutrinos as the thing. So for thermal warm dark matter, this is something like gravitinos. You've got a thermal distribution, Fermi-Dirac distribution. You get suppression by a factor of 100 due to disappearance of degrees of freedom from when it was produced till today. And so you get it, and it's also cooled by that disappearance of degrees of freedom. This is the gravitino. And sterile neutrino warm dark matter is different. You don't produce it at very high temperatures. You still produce it from a thermal thing, which is the active neutrinos. They scatter to the steriles. So you just get a suppression of the full thermal distribution by a factor of 100 to get the right abundance. And that's to satisfy the Kozak-McClellan bound, as I mentioned. And you also get some cooling because after it's produced, the quark-hadron transition happens and other degrees of freedom go away, like electrons, positrons. And so you get a little bit of cooling due to that. And this is the Dodel-Woodrow mechanism. And then you can also have resonant production, which enhances at low momentum modes. And so the Shih and Fuller distribution is down there, okay? So all of these things have different properties as to how they free stream. So when you work it all out, there's certain relationships, and I won't go through them in detail, but basically the mass of a sterile neutrino through the Dodel-Woodrow mechanism is about 4.5 times that of a thermal warm dark matter neutrino at the keV scale, and it actually separates more if you go to higher masses. And so like a 2 keV thermal, which is our golden number, we get 11 keV for a Dodel-Woodrow case, and for Shih and Fuller, it actually works out to be about 7 keV. This is all worked out in these relationships are discussed and worked out in these papers here, including the Numadov one. So this is, you want to take this distribution and calculate what the suppression of power is. And so here, here T nu S over T CDM is the ratio of the cold curve to the warm curve, or the warm curve over the cold curve. Okay, so this is how things are suppressed at small scales, a small wave number, which is where things are here. Okay, so I'm gonna, considering the time, I am gonna skip over to X-ray astronomy, because there's other ways to produce this, and that's what the other slides are about. Let me just mention there are ways of getting 5 keV thermal warm dark matter. If, for instance, you're constrained by small scale structure constraints, there are ways to get a 5 keV thermal equivalence with a 7 keV sterile neutrino. That's the reason why 7 keV sterile neutrinos of interest is the next topic. Okay, so as I mentioned, back in 1999, Chandra and XM Newton were launched. In 2000, they started getting results. In 2000, 2001 is where the sterile neutrino as a dark matter candidate really started taking off. And the reason why it's relevant is that the sterile neutrino is not purely sterile. To get produced, it has to mix with the active neutrinos, and that mixing allows for this loop decay diagram to be non-zero. It produces a radiative decay. So the thing that's mostly sterile, of course, in free space is actually a mass eigenstate, and it decays to a thing that's mostly active and a photon. And the energy of the photon is half the rest mass of the sterile neutrino, or the mostly sterile state. And the decay rate is very slow, 10 to the minus 28 per second. And that is just specified by the masses and mixing angle relationships in order to get the right abundance. But this is really small number. The number of particles in a cluster of galaxies is like 10 to the 80, maybe 10 to the 78. It's really large. So you beat this number by this number, and in the end, you get about 10 to the 48 dark matter particles decaying every second for these parameters of this candidate signal that exists. So back in 2001, when I was looking at constraints on sterile neutrino dark matter, X-ray astronomy was the best thing. And we looked at a future experiment called Constellation X, which was expected to have several telescopes in space to give more collecting area of photons. And well, we kind of hedged our bets and said, well, if you don't get Constellation X, and we haven't in the past 19 years, we said an exposure equivalent to Constellation X could be obtained by a stacking analysis of a number of similar clusters. And so that was done. 13 years later, the Chandra X-ray science team at Harvard, at the Chandra X-ray Science Center, stacked 73 clusters with a 6 megasecond total exposure time, and saw an unidentified line in the spectrum. They saw it with 2 different instruments. They actually, for part of the analysis, used Chandra towards Perseus, but then they looked at XM Newton and MOS, XM Newton PN and MOS detectors, which are 2 different direct detectors. Simultaneously, a group working with XM Newton data saw the 3.5 keV line in Andromeda observations with XM Newton, and also Perseus observations with XM Newton. The 2 teams apparently discussed that they actually had evidence for a line, but didn't tell each other as to the position. So, and so they independently found the results. And so one of the things that always is discussed is metal lines. And back in the original papers, they showed that potassium can't be a significant contributor to the flux. This is the detected flux. Potassium is the black and green lines. They're very low. You'd have to enhance the abundance of potassium by a factor of 20 or so to get the flux, and it's not expected. Also, argon doesn't work due to other partner lines. I think the best non-new physics observation, or best non-new physics explanation for the lines is charge exchange. You can have sulfur capturing an electron, bare sulfur. This is sulfur that's 16 times ionized, capturing a donor electron from what would be hydrogen likely, because most of the plasma is hydrogen. It could capture that electron and produce an X-ray. And that's called charge exchange. And there's a charge exchange transition between 3.44 and 3.47 for the highest transitions of sulfur. And one thing is that, yes, that could definitely be the origin of the line in clusters, but the energies don't perfectly match, and it's a bit lower than the observed energies of the charge exchange. So it's been seen in those original things, and since then it's been seen in a bunch of places. And I'm not going to go over all of these because there's a lot, but it's been seen originally right in the Andromeda observations with XM Newton. It's also been seen in Perseus with 3 different telescopes, XM Newton, Chandra, and Suzaku. It's been seen in 8 more clusters at greater than 2 sigma significance. It's been seen in the Milky Way Galactic Center by Boyarsky's team and others. It's been seen in the Milky Way Galactic Center with Chandra, and more recent work by Hoffman and Weg. And it was seen in new star observations of deep fields at 11 sigma, which is crazy. But it's thought to potentially be an instrumental line, which is what was originally interpreted as. So it's not clear if that is certainly from the sky. And it's also been seen in the Chandra deep fields at 3 sigma. There's actually an extension of the Chandra deep field analysis that will be coming out soon that doesn't see it, actually. So and places a limit, although the limit is still consistent with other constraints. So this is where the signals lie in mixing angle versus mass space. I was inspired by the CMB plot I showed at the beginning of this lecture by Wayne Hu. Wayne was one of the first to do really nice plots in the cosmology community. Basically, these are the things with bigger errors or fainter, the things with better errors are stronger to see. So anyway, so this is where the signals sit, and the lines are where there's limits. So you have to, the limits require you to be lower than those lines. So there is tension, and the tension existed with work that we did in Irvine. The best limit here is from Shosaku Horiuchi when he was at Irvine. This limit sits here. There are now a couple of stronger limits. There's a few that are problematic that basically do not see the line and are claimed to completely exclude it. However, there's issues with them. The 1 megasecond exposure of Draco didn't see the line, but the team that proposed the observation concluded that it wasn't necessarily inconsistent with the dark matter interpretation. I still think it's problematic that this deep exposure didn't see it. If you look at where their constraints are, they're pretty low. There's also a stacked galaxy analysis. If you look at the continuum, however, in that analysis, it has features that are as big as the signal, the uncertainty in the continuum that they infer. So it's not very convincing. And then more recently, there's work by Desert, Rod, and Safdie that used 30 megaseconds of XM Newton data and used a very narrow energy window in their analysis, 0.5 keV. The energy resolution of these instruments is 0.2 keV. So this is the Desert, Rod, and Safdie analysis, and they show the spectrum and they show the expected line, and note that only half a keV in energy range. conclude that the decaying dark matter interpretation of the previously observed 3.5 keV unidentified X-ray line, exclude the required decay rate by more than an order of magnitude. Okay, sounds reasonable because that looks like pretty inconsistent. So they place this constraint, and it's over here. And actually, this line would go to negative values, which you can't do on a log plot because they actually have a negative residual right at the 3.5 keV point, which may indicate something. But anyway, they bound it from below by the expected containment. So one of the things that they didn't include is that one of the things that's problematic was that they had a density that's fixed and a profile that's fixed. In particular, this number, the local density of dark matter, is unknown to 30% by some estimates. So that changes your uncertainty quite a bit. And they also they did a varying of the profile, but they didn't actually take the most conservative profile that is consistent with the data. So that was also an aggressive step on trying to get a very strong limit. And so another thing they did was not include known lines that exist within the spectrum. There's one known line at 3.3 keV and another known line at 3.7 keV. There's this one and this one. And the 3.5 keV line is there. And I just took their data that they published. I didn't download the 30 megaseconds of data and do all of the analysis, but certainly if these points and errors represent the data, and if you look for the 3.3 and 3.7 keV lines in that data, then you actually detect them at various levels of significance in the MOS and PN data. That fits better to have those two lines than to not have them. And then the presence of the 3.5 keV line is certainly relaxed. And so it actually is right, so these are the various lines. They're preferred by 4.3 and 2.8 sigma for the PN and MOS data. There's plenty of room left for the 3.5 keV line. This inclusion of these lines relaxes their limit by a factor of 8 to 9. Okay, and then it begs the question: why did we only look at half a keV data? Certainly, it looks like maybe there's a line over here and a line over here. Other things are going on. Maybe we should look at more than half a keV of the data. And I'm going a little bit over time here, but basically the DRS limit, the Desert and Company limit, is actually here once you relax the dark matter profile uncertainties and the presence of the lines, which gives, so the dark matter profile uncertainties are about a factor of 3, and the presence of the lines is a factor of 8 or 9. So overall, a factor of 20 weaker. Their claimed exclusion was down here at the 10 to the minus 12 level, but really it's about the 2 times 10 to the minus 11 level or so. So is that still the best limit? Who knows? So they've got published in this journal called Science, which purports to be the best, among the best journals in the scientific world. And let me just tell you about a little bit about what's going on with this journal. So here's their concluding sentence in the paper by Desert and Company. Our analysis rules out this dark matter interpretation because they exclude the required decay rate by more than an order of magnitude. Okay, so I wrote a technical comment on their paper and submitted it to the journal Science because, first of all, they didn't include those dark matter uncertainties, and that relaxes their limit by a factor of 3. Some of those dark matter uncertainties, namely the local density of dark matter in the Milky Way halo, that wasn't included in their analysis. So when you include known lines at 3.3 and 3.7 keV, you find evidence for them, which I showed, and that relaxes the 3.5 keV line by a factor of 8 to 9. Combining both things, which are different model dependencies, you get a factor of 3 times 8, and let's just say that's a factor of 20 weaker, right? And then that quoted. So the 2 more senior authors emailed me a response saying, we do not believe that you're correct in treating the stacked data, and leads to the improvement that you quote. However, they agree that my figure 2, which is the relaxation of the limit by a factor of 20, is correct. So I'm not really sure how those two sentences are compatible. The editor, Keith Smith in Science, on my comment said, the Desert paper already discussed it and tested those issues. So the authors say that I'm incorrect in the method, but apparently they already tested those issues. Therefore, we are rejecting your comment. So this is an amazing situation because both the science editors and the authors admit that the claim is a factor of 20 weaker, but they do not correct the record in the paper or in the journal with a technical comment discussion. And there's still time until the 27th of June for me to submit a letter to this 3 months after publication to Science. And I'm just going to have to explain the situation, which is a little bit odd. Anyway, I didn't want to end on a battle. Let me just show what the sky could look like. If we really have a signal on the sky, either in gamma rays or X-rays eventually, we're going to start being able to do dark matter astronomy, either in X-ray or gamma ray. You would get a flux map, and you would also get a velocity map of the sky, because our galaxy's galactic disk is rotating relative to the halo. So we'd get a Doppler shift map, and that actually would also see structure in there. And the structure is different than gas. So gas is associated with the disk, so the velocity information is different. So you can get this kind of dark matter velocity spectroscopy information, which was pointed out by John Beacom's group originally. But it turns out that, you know, new statistical methods are great, including the Softy analysis. They claim to be doing new things by looking at only very narrow windows of energy. And also this dark matter velocity spectroscopy is a great method. However, just the brute force methods of counts is also important. So one of the things we discovered is there's a proposed, and sorry to be going a bit over, but this is really amazing, that there's a proposed experiment, a proposed X-ray telescope by the Chinese space agency and X-ray astronomers in China working with European X-ray astronomers, called EXTP, and that's here, Enhanced X-ray Timing Explorer. It has an instrument that if I were to design a dark matter search experiment, that's it. It's sitting down here, called WFM, and it's right here, and it looks like it has no optics. It's just an exposure of an X-ray detector to the sky. So basically it has a view of I forget the exact number of steradians. Is it here? No. Anyway, it's something like, you know, there's 4 pi steradians on the sky, and it's, I think, about 4 steradians of it. Something like that. So anyway, because you have this enormous view of dark matter, you get 1 million counts if the 3.5 keV line is due to dark matter, 100,000 to 1 million. So anyway, I'll stop there. Just I wanted to get to a more positive note that this kind of sensitivity from the WFM instrument, the XTP, which is supposed to launch in a year or two, is going to be one of the most sensitive probes to dark matter. Outside of the 7 keV thing or 3.5 keV thing, it's going to really push down the limits, and for sterile neutrinos being the dark matter. So thanks.
All right, thanks, Kev. There's a few more questions in the chat. If you want to take a look.
Okay.
Actually, lots more questions in the chat.
Oh.
2 at least. Actually, I think one that maybe, I don't remember if you missed it. This is getting back to the N-body simulation from Santa Cruz, from Sorab. Is each bright dot a source of light in these simulations?
It would be if the dark matter is decaying or annihilating. Yeah. So when in this figure, we've actually used the latest hydrodynamic simulations of the Milky Way. So it includes baryonic effects as well. So this flux map is actually from the fire simulations, the dark matter in the fire simulations. So each of the substructures is bright on here. However, they're not quite as. So this is a projection. If you're looking at the sky. If you're looking at the sky in projection as you're sitting in the Milky Way, is different from looking at it from outside as it's plotted in that movie. Yeah. Let's see what other questions here. What is the question left for sterile neutrinos? Is the free streaming length too long to produce small structure profile? Yeah, so that's kind of very quickly went through these models. You could actually, so the sterile neutrino as the Sheaf-Fuller mechanism and the Dodelson-Woodrow mechanism, definitely the Dodelson-Woodrow mechanism, if it produces 100% of the dark matter, this was the point of the Horiuchi paper back in 2013, the Dodelson-Woodrow mechanism is ruled out by X-ray astronomy and structure formation back in 2013. However, Dodelson-Woodrow could produce a fraction of the dark matter and produce this signal, the 3.5 keV signal, which is actually completely allowed because you only need 13% of the dark matter to be sterile neutrinos to produce the signal on a 3.5 keV line. And then you would have a cold plus warm dark matter situation. But also you could have 100% of the dark matter be a 7 keV thing by producing it through a high energy mechanism, which is a thing that I skipped over. Basically, by having a very high scale production mechanism, it can be much more cold. All right, the other things, referring to a previously asked question, I'm not sure if you answered it. How does CMB distinguish between a normal hierarchy and inverted hierarchy? Right, so what it does is it measures the neutrino, it measures the sum of the neutrino masses. So it doesn't actually distinguish between the two. It measures the sum of the neutrino masses, and then what the extra information as to what the ordering is coming from long baseline results.
Mm-hmm.
How many sterile neutrinos are needed in a model of dark matter model and neutrino oscillations? 3 is the answer. Yeah, I've read that the standard scenario is 3 sterile neutrinos. Right, so in order to have dark matter plus neutrino oscillations, you need 2 massive sterile neutrinos to produce the atmospheric and solar scales, and then one is extra and could be the dark matter.
In that case, would the lightest neutrino be massless?
Right, it would be close to massless. It wouldn't be perfectly massless, but very, very, very light.
So you're basically introducing 3 right-handed neutrinos. 2 of them pair up with the active neutrinos to make mass eigenstates, and then, wait, maybe I'm wrong.
The third one is still contributing to the mass of the lightest one because of just because it's mixed with the lightest one.
Oh, it's Majorana still.
Yeah.
Wait. Okay. Okay. Oh, that's cool, actually. Okay.
It's just very, very light. Like I haven't calculated what it is, but it's 10 to the minus 10 eV or something.
But then the active neutrinos are Majorana, and the extra 2 sterile Majorana neutrinos are just like much heavier.
Right.
Okay.
Yep.
Okay. All right. Great. So I'm not seeing more questions popping up rapidly, and it's already getting kind of late. So let's say a big thanks to Kev for these awesome and fascinating lectures that he's given this week. And